And the next speaker is Jérémy Thibault from EPFL.
Okay, hi. So thank you for being here. I'm Jérémy. So this is work done with Basile and Cătălin when we were at MPI-SP. And today I'm going to talk about a proof technique that we've devised to help us verify low-level secure compiler backends. And this proof technique, we call it blame-aware recomposition. So I want to start with a bit of background and context. So right now, many systems are still written in unsafe languages like C. And it has some issues. It has many undefined behaviors, buffer overflows, use after free, double free, all those. And they can lead to devastating attacks. For instance, Microsoft and Chrome report that 70% of the high severity bug that they encounter are memory safety vulnerabilities. And unfortunately, it's not really realistic to replace all that unsafe code by nice safe code. So instead, something that has been proposed often is mitigations, and one of it is compartmentalization. With compartmentalization, we start by splitting our source code in different compartments that are protected to from each other and interact through protected interfaces. This code that is compartmentalized gets compiled to machine code that is still compartmentalized, that might be linked with some external context, low-level libraries, for instance, that might already be compartmentalized. And then there is a compartmentalization mechanism that protects all of this. Hopefully, this compartmentalization mechanism is strong enough to preserve security properties of the source. And that's what I would call a secure compilation chain. So in the past, we've done some work on formally verifying secure compilers that use compartmentalization. And we prove a theorem that basically states that low-level finite executions can be explained in terms of the source. And that corresponds to the preservation of safety properties. So just to make it a bit more concrete, if at the bottom you take this entire program and it produces a finite trace M that records calls and returns and their arguments, then through a process called back translation, the theorem states that we can use a back context, a source equivalent of the low-level library, and that we can link it with the source code and produce the same trace. So we've built some compilers and we've verified that they satisfy something like this, except we didn't. So actually what we did is we stopped the verification just before reaching that very low level. And instead we have verified something at an intermediate level, which has still intermediate code that is compartmentalized. It still has a context that is compartmentalized, except it's not as concrete as a real backend. For instance, this intermediate level uses a block-based memory model, while in the concrete backend, we would prefer to have a flat memory model, which is closer to reality. In this model, the code is separated from data, while in practice, code actually lives kind of in the same memory space, and there are protection mechanisms to isolate it. And what this means is that in the intermediate language that we considered, we only had an abstract compartmentalization mechanism that was built in the semantics and was acting more as a specification of the actual behavior of a concrete implementation. Instead, we would want to actually verify that concrete implementation of the compartmentalization mechanism. So you might ask, why did we stop here? Well, we stopped because the proof technique that we were using was not really working for us at a lower level. So I will now explain a bit this proof technique. So basically, the idea was at this intermediate level, we were starting from a compiled program, P down arrow, linked with a low-level context, CT, that produces some trace. And as I say, we need to prove that there is a source context that we will call CS that can be linked with P and produce the same trace. So what we did is actually do a back translation to get a CS, but also a new program P prime that produces the same trace. And that's not the result we want, because we want, instead of P prime, we want P. We would use compiler correctness here to go down to the intermediate level by compiling this CS P prime. And then we would have a step called recomposition that takes the P compiled from the left and the CS compiled from the middle, put them together. And then we see that everything is compiled, and we were able to go back using compiler correctness to the source. The reason we are using a proof technique a bit involved like this is that it really allowed us to reuse existing compiler correctness results instead of having to redo them from scratch. Unfortunately, recomposition that we use here at the intermediate level is the source of the issue, and we cannot use right away at a lower level. So why is that? For this, I will even explain a bit how we proved recomposition. So again, we start from two executions of different programs, but that share the same trace, and we obtain a recomposed execution. Concretely, we start from, we split our programs in an A part and a B part, for instance, and we start from A1 and B1 on one side, A2 and B2 on the other, and we want to take A1, link it with B2, and show that they do the same trace. So if A1 and B1 and A2, B2 linked together produce the same trace, we want to obtain A1 from the top, linked with B2 from the bottom, and show that they generate the same trace. We are using a very simple, conceptually simple so we are saying, imagine, for instance, we're starting with in the A, that if A starts with a silent step in the top execution, while in the middle, we are also starting in A1, and we were proving that we can do the same silent step. And we were proving that we could repeat this until we reach an event. In the first execution, a call from the A part to the B part. And then we are saying, well, because the two executions produce the same trace, we can reach a point where we're going to do the same call in the bottom execution. And that means we can prove that A1, B2 performs the same call. And this time, because we're calling B, we go to B, and we repeat the same argument with silent steps in B this time. So we do the same again. And then we encounter a return. Same reasoning. There is a return at the top. And so there is a return in the middle, etc., until we produce the entire trace again. So this is nice, but this doesn't actually work in a concrete level. And for instance, this is because of these silent steps. So here, when the A1 part steps, it cannot actually know about whether it's linked against B1 or B2. Otherwise, there would be ways for it to make a different choice. And so do different things, and we could not reproduce the same silent step. Said another way, it means that cross-compartment observations must be recorded on the trace. And that's really not possible if we only record calls and returns at the lower level. So for instance, because we have a flat memory space, compartments are able to observe the allocation pattern of other compartments. So they know how many allocations the other compartments have done, and they can do different things based on that. Similarly, all code is usually laid out sequentially, and so it's quite easy to observe the size of the code of other compartments. Finally, there's no distinction between code and data. So code can even be read directly if you want, without any additional protection. But the thing is, these are not really about safety properties, which are the criterion we care about. Those are about code confidentiality. And so we thought there should be a way to make the proof work. Our contribution is to indeed extend recomposition to this lower level. And the key idea is that we can characterize these behaviors as these behaviors that observe things about other compartments as undefined behaviors with respect to an overlay semantics, which is represented by this funny arrow here. So the overlay semantics we introduce is just the same as the low-level semantics, but it prevents all these recomposition breaking behaviors, such as reading the size of the code, reading code directly. And what we mean by undefined behaviors with respect to this semantics is that it's behaviors that are allowed in the low-level semantics, but not in the overlay semantics. The second insight is that recomposition manipulates 3 compile programs and 1 low-level program that we will discard. And so maybe it's not too bad if that low-level program does undefined behaviors. So this looks in the end a bit like this, except that here we have 2 different semantics for the low-level syntax, and one is more restrictive than the other. The overlay semantics is much more restrictive. So blame-aware recomposition that we introduce looks very similar to the previous recomposition, except that when we manipulate only compile programs, we are reasoning in the overlay semantics. On the other hand, when we're manipulating a non-compile program, we're reasoning with the low-level semantics. But we add one more condition. Either that this execution has no undefined behavior, meaning we could actually reason everything in the overlay semantics, and in that case, it reduces to the previous recomposition proof, or that the undefined behaviors happen only in the context part. So when you have this property, you can actually retrace the steps of the original proof steps, this time between the overlay semantics and the low-level semantics. And you can prove again the same criterion, and then by vertical composition, you can get it for the entire compilation chain. However, before I talk a bit more, just some limitations of this approach. Precisely characterizing all the behaviors that break recomposition is hard, so we are not able to do it. For instance, take this piece of code, it allocates, it calls another compartment, it allocates again, and then it does different things depending on how many things the intermediate compartment has allocated. Well, this is very hard to find to track in the overlay semantics. We would need very fine tracking of pointers, and so we decided to not do it. Instead, we use additional lightweight protections in our concrete implementation of the protection mechanism by using a custom allocator that separates memory spaces to hide the data layout of each compartment. That's not strictly necessary to obtain the top-level theorem, we think, but that makes the proof work much better. So we apply this technique to an existing micro-PriSC backend that was only previously tested. So it's a programmable tagged architecture where tags are used to enforce compartmentalization. And we only needed to do very slight modifications related to the memory layout. Our proof technique, to prove blame-aware recomposition, we have a 3-way simulation that is very similar to the one we are using for recomposition. So we have proven the main lemmas for this recomposition. Not everything is finished. This is still ongoing work. But what's important is that when we actually prove these main lemmas, we have to reason about tags. We have to reason about the compartmentalization mechanism we just implemented. So that gives confidence that we implemented this micro-PriSC correctly. So we're missing still a few things. Some results on big vectors. We have some performance issues with ROC. And we are and some results to tie everything together. So just to conclude, we're working towards a verified low-level backend for a secure compiler for a compartmentalized language. This has a flat memory model. Code is readable. You can even execute data if you want in that language, in that low-level backend. For this, we use blame-aware recomposition, a novel proof technique that uses overlay semantics to characterize some behaviors and undefined. And we still need some additional protections, unfortunately, to make the proof doable. So some questions we'd like to explore. Can we get rid of these unnecessary protections for the criterion we care about? Or on the other hand, can we generalize to a much stronger security criteria since we have additional protections? So I think that's all for my talk, and I'd be happy to answer any questions.
No questions? No? So, okay.
I wanted to ask about your overlay semantics. Does it change the events on the trace, or is it the same trace for all levels?
It is really the same trace, and this is very useful because that means we can reuse things like the back translation to go back to from a low-level execution. We're using the back translation to get something in the overlay semantics by back translating and then recompiling down.
So I too have a question. But you at some point you had a slide with the problem of information leakage through malloc, and essentially with too strict semantics, this would have prevented using any malloc. And you use this separate allocation scheme. There was another method used in variants of comcert to give low-level flat semantics to things, by people like Pierre, for instance, which was to say that behavior is defined. Basically, if it defines the same behavior in all possible concrete memory allocation layouts. Have you considered doing that?
Well, I believe if we were to do that, we would exclude a lot of programs that we would want to consider in our program. So I would assume that many low-level contexts would not have defined behaviors with this kind of semantics.
Okay. No other question? So we can thank the speaker again.